Combinatorics is a part of probability theory, but we put it here separately. And combinatorics has to do with how many different ways can you combine things. For example, if you have 5 people and you want to pick out 3 of them, how many different ways can you do that? Or if you have a box of colored balls, how many different combinations can you draw from that? Things like that is covered by combinatorics. When doing combinatorics, it's useful to use some shorthand for symbols. And that's the first one we want to look at is a factorial. And that you write as this. So this is called a factorial. Per definition, this means n times n minus 1 times n minus 2 down to 1. So here n is a natural number. So for example, 5 factorial means 5 times 4 times 3 times 2 times 1. Of course, you don't have to write it 1, but it's easier to remember that way. So this is 20 times 6, so 120. And for example, 1 factorial is just 1. 0 factorial you define as 1 to make formulas work also in this case. Okay, so that's the factorial. Another thing you define is a binomial coefficient. And that you can define in the following way. The symbol for that is this. And this is not a fraction, so there's no division sign here. This is just 2 numbers we put under each other. Per definition, this means n factorial divided by k factorial multiplied by n minus k factorial. Okay, so for example here, if you have 5 over 3, we could say. According to this definition, this means 5 factorial divided by 3 factorial. And this is 5 minus 3 factorial. So this is 5 times 4 times 3 times 2 times 1. This is 3 times 2 times 1. And here it says 2 factorial, so this is just 2 times 1. Before we calculate this now, it's a good idea to simplify, because otherwise it will be large numbers. So you see this can be crossed out to that. And this 2 here we can cross out 1, 2 here. So we have 2 left. So it's 5 times 2 and 1 down here, so it's 10. So this is how you calculate the binomial coefficients. And the reason for defining these strange looking things, factorial and binomial coefficient, is because they arise quite often in combinatorics. So it's useful to have a shorthand for those. Combinatorics can arise in many different situations, but one situation that is particularly useful to use is when you have a urn or a box or a bag of different colored balls, because this can be used to identify many other situations similar to this. So for example, if you have now some different colored balls in a urn or in a jar or a box or whatever bag. So let's make some different colored balls here. They should all the balls should be identical, even if I don't draw them like that now here. Let me draw some. Okay, I only draw 3 now, but there should be many more, of course. So I have different colored balls here. Or many, of course, but there could be many more. Okay, so I pick balls one at a time, or I can also pick at the same time, but so I pick balls from here with or without replacement. And that means that when I draw a ball, if I draw it with replacement, after I draw one ball, I put it back before I draw a new one. So I have a chance of drawing the same ball several times. So if I draw first the red, then I put back the red, so I have a chance of drawing it again later on. Without replacement is, of course, then you draw a red ball, you don't put it back when you draw the other balls. So you can only draw the red one once. Okay, so that's with or without replacement. And then can it be an ordered or unordered draw? Or unordered. Okay, so an ordered draw means that we care about the order in which we drew the balls. So for example, if I first draw a red ball and then draw a yellow ball on the second draw, if I consider an ordered draw, that I consider as a different outcome than if I got a red on the second and a yellow on the first. So these two outcomes, this is one outcome. This means getting a red on the first draw, yellow on the second. That's a different outcome than this one, a yellow on the first, red on the second, if I consider the draws to be ordered. If I consider the draws to be unordered, I don't care about the order. So then I consider these two outcomes to be identical. Because I only care about maybe which colors did I draw, not in what order I drew them. So in this case, we can draw balls from this urn in 4 different ways. We can draw it with replacement or without, and we can draw it ordered or unordered. Okay, and then there are easy ways to calculate how many combinations you can get. So how many combinations can you get now with or without replacement if you draw colored balls from the urn? Okay, let's first just write the formulas for that. And then we can see some examples of it and comment on the formulas. So now we have these 4 situations: ordered with replacement, ordered without, unordered without, unordered with. So all 4 combinations. Then we have formulas for these cases. So let's say that we draw K balls. Okay, and the ball contains, the urn contains n different colored balls. Then we can write the formulas in the following way. If we draw ordered with replacement, then the number of outcomes we can get if we draw K balls from urn containing n balls is n raised to the power of k. Like I said, we'll come back to motivating these formulas. We'll look closer to them. Just write it down now for the moment. And the second formula is given by n factorial divided by n minus k factorial. And then it's the binomial coefficient n over k. And the final example, also a binomial coefficient. So already here we see a reason for factorials and binomial coefficients, because they are right here in the formulas. These formulas would be much longer if we written without using these symbols, factorials and binomial coefficients. Okay, so let's go through these cases one at a time. So let's first look at the example of ordered with replacement. So let's say we have 10 persons. And they are having a wine tasting evening. They're testing wine bottles. And they're having a lottery, and they're seeing a person will win bottles. They have 3 bottles they will lottery out. So this is some ugly drawn bottles, but okay. So you have 3 wine bottles that they want to give out randomly. Same person can win several times. So the same person can win all 3 bottles. How many different outcomes of the lottery is there? Okay, so in the first situation here, you have 10 persons can win the first bottle. But also 10 persons can win the second bottle, because you can win several times, and also for the third. So 1,000 different outcomes. For example, person number 1 winning all 3, or person number 1 winning 2 of them, and person number 2 winning 1, and so on. So that 10 to the power of 3. But this is just an example of ordered with replacement. It's ordered because it matters in what order the person are winning. So if the first person number A wins first, and then person number C wins, and then person number B, and then person number C wins, this is something different than person number B first wins, and then the person number A then wins, and person number C then wins. So these are two different outcomes, because the bots may be different, so if which one they win matters. Okay, so we can think of it as a draw. We have a huge urn. So similar to this situation, we have a big urn, and we have 10 persons. So 10 different persons. Okay, so you have 10 of these here. And now we want to draw one of these persons. Okay, so we draw one of them randomly. And the first person we draw will win the first bottle. And then we put that person back, because the same person can win bottles several times. Can win the second bottle also. Okay, so draw again, see who wins the next bottle, put that person back, and draw a third person, see who wins the third bottle. Of course, in reality, we don't draw persons from an urn, but we could, the situation is equivalent to that. So you can just think of it as this instead. So here we have a draw of 3 persons from an urn among 10 people. So we're drawing 3 persons, k is equal to 3, and we have a total of 10 persons. And it's ordered because the order in which we draw these persons matter. So we draw person number A first, then B, C, it matters. So it's order draw, and with replacement, because after we draw a person, we put that person back, because the same person can win several times. Then we have the formula like we wrote on the here. You see we have n to the power of k. So that means we have 10 to the power of k, and k is 3. And that was the same we arrived here, but just by pure reasoning. So this is an example of order with replacement. So you see here that we can just make a similar situation with an urn drawing things. Then we can figure out how to do it here. Then the next example will be ordered without replacement. Okay, so let's take an example here. How many different words can you write of 7 letters? So let's take A, B, C, D, E, F, and G. So you have 7 letters. And how many different words can we write by this? And by word, we don't mean a word having any meaning. We just mean ordered combinations of letters. For example, and there should be 3 letters in the word. So for example, B, C, F, that's a word. And C, F, A, that's another word. And for example, F, C, A. These 2 words are different because the order here matters. So these are 3 examples of 3-letter words we can write. So how many different words can we write? In the first position of the word, we can have 7 possibilities. And okay, let's say without replacement, because we're only allowed to use each letter once in this example. So in the first position, we have 7 possibilities. Use any of the letters. And for each of those combinations, we have 6 letters remaining, because we have, when you choose the first one, there's only 6 remaining. And then it's only 5 remaining. So we have a total of 7 times 6 times 5. Okay, so that's how you can calculate it. So this is 30,210. This is ordered without replacement. So let's look at here at what we had. order without replacement, then we have this formula. So we have that n minus k factorial. And what is n? N is the number of letters we have. And k is how many letters we pick free. We have a 3-letter word. So we can think of now having an urn with letters. We have A, B, C. So you can think of a letter biscuit or something. You're drawing from an urn. And we have without replacement and order. We draw them. Then we have 7 factorial here. And 7 minus 3 factorial. That's 4 factorial. So this is 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4, 3, 2, 1. You see here you can cancel that to that. This is just 7 times 6 times 5. But that's just what we arrived at here. So in this case we have an ordered draw without replacement, since we can think of this as drawing letters from an urn without replacement. Then the third example, we have an ordered draw without replacement. So let's say that you going to pick out among 5 persons. So we have 5 different persons. Let's call them A, B, C, D, F. No, not F, E. Okay, so we want to pick out 3 of these. So we want to pick out 3 persons out of 5. Okay. So how many different ways can we pick out a group of 3 persons? Here it doesn't matter with which order we pick them, because we are only interested in which 3 persons we take along, if we're going for a trip or whatever. So in this case we consider it to be an unordered draw. And it's without replacement, because we can't pick the same person several times. Okay, so how many different combinations are there? Then we can see here that we have, let's first pick them. Let's first take a special case where the order does matter. Okay, so the order does matter. How many combinations do we have then? Then from just the previous example, we have that we have 5 persons and we should pick them. So we have 5 minus 3. So this was the formula used in the previous example, because we picked an order draw without replacement. Then this would be the formula. Okay, so we have 5 factorial, picking 5 persons, and we pick 3. But then, now we will get, like for example, we get A, B, E. That's a group we could have. But now we are considering this to be a different group from this one, for example. But we want to consider this to be the same. Then we have to group these together. That's how many words can we form from these 3. So we can have A on the first position, the second position on the third, and we can have B on the one on the remaining, and so on. So we can have, in the first position, we have 1 in 3 possibilities. And remaining on the second position are 2 then, and then 1 on the final one. So we have 3 factorial different words we can write with these 3 letters. So we should group this together, meaning that we shouldn't consider this group to be different. So we have to divide by the size of the group here. Okay, so the sizes of the group we have to divide by, because we are grouping them together. And this will give us this number. But what is written here is just binomial coefficient 5 over 3. Okay, so this is just 5 over 3. Or if you calculate this, this is 5 times 4, 3, 2, 1, divided by 3, 2, 1. And this is 2 factorial. So you see that we can cancel that to that. So this is 20 divided by 2, this is 10. So it means in this case we have 10 different groups of people we could pick. But we can also go back here now to the example we had before. Unordered without replacement. That was the binomial coefficient. So that's what we just arrived here, reasoning differently. Okay, so if we have an unordered draw without replacement, we can just use the binomial coefficient. Because here again, we can think of it as picking among 5 persons from an urn. And we're picking 3 without replacement. And therefore it's given by this formula. And the final example is unordered with replacement. So if we go here now, unordered with replacement, and we have this formula here. So we'll use that formula later on now. But let's see, just take an example first. Okay, so let's say we have, you are invited to dinner, and they are offering cookies, and you have 7 different types of cookies. Okay, 7 different types of cookies. There are infinitely many cookies of each type, or there are so many so you can eat as many as you want of each type, or pick as many as you want. But there are 7 types of cookies. Okay, so do you want to take 4 cookies at once, or at the same time? Take 4 cookies. But you can take the same type of cookie several times, but you want the number of cookies you take to be 4. So you can take 4 of the first type, or 2 of the first type, or 2 of the second, or whatever. You choose 4 cookies. So this is an example of unordered, because it doesn't matter in which order you pick the cookies. You can take type number 1 first, or type number 2. It doesn't matter. You just end up with 4 cookies. So you're only interested in what kind of types you got. But what is replacement here? Yeah, replacement is not here that you replace the cookies you took, but instead you think of that you have 7 boxes of cookie types. Okay, so you have 7 boxes of cookie types, and now you want to pick one of these 7. Okay, so first I pick this one maybe, and then I pick this again, and then I pick that one, and then I pick this one. So you take 2 cookies from that one, 1 from that, and 1 from that. And with replacement here means that you can take the same box, take from the same box several times. So instead of taking from a box, you could think of here that you have a urn with balls. So you have 7 balls. So you pick a ball, for example, you pick a red one here, or you draw a red one. So let's say you pick this ball. A red one means that you take a cookie of type number 1 from the red box. But then you put that ball back, because you want to be able to draw the same type again from the box here. So you're not taking replacing cookies, but you're replacing the options of what type of cookies you can take. So you can think of it as you're picking 4 balls with different colors, and which color says from which box you should pick. So you can replace. Therefore, it can be thought of as an example of unordered with replacement. Okay. Then it's a little bit tricky to calculate here now without using this formula, because in this situation it's unordered replacement. You can pick this one several times. It's not so easy as we had these letters where we can group them, because the group will be of different size. So instead of calculating in an intuitive way, we just stick to the formula instead. Okay, so let's trust the formula and hope that it gives the correct answer. So we have 7 different types of cookies, and we pick 4. So what will this be then? It will be 7 plus 4 minus 1, and then we have 4. So this is 11, 10. And then I almost write a fraction here. No, it's not a fraction. It's 10 over 4. So this is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. you see that factorials become extremely large. So if you try to put into calculator, it's sometimes difficult to calculate. So you really need to simplify your expressions before putting into calculator if you want to do that. So this means 10 factorial, 4 factorial, and then you have 10 minus 4 factorial, so that's 6 factorial. That's the binomial coefficient. So now you see here you can cancel that to that. That simplifies a lot. And here you have 4 times 2, that is 8. And 3 here, you can cancel out the 3 here. So you have 10 times 3 times 7. So that's 210. So 30 times 7, 210. And here we only have ones left. So you can pick cookies. If you want to pick 4 cookies from 7 different types, you can pick them in 210 different ways. If you do it, you can pick the same type of cookie several times. Okay, so let's go back to these formulas here. This can be proven. So one can prove these formulas. But let's not do that here right now, because from the example we have seen so far, it's quite obvious how you should prove them. Or you can, if you look at the book, I have proven them there, so you can look there. But looking at examples for the first 3, it's not so difficult to generalize what we did there, examples to prove. The final example is a little bit more tricky, this one. But the proof is also in the book if you want to look there. Now the final thing we'll do is to combine combinatorics with probability theory. So now we have talked about binomial coefficients and factorials. We can try to figure out probability distributions in a little bit more tricky cases. The first one we'll look at is called a binomial distribution. And it's a complicated name for something that is not that complicated really. So a binomial distribution, you have a binomial distribution if you have 3 conditions, the following 3 conditions satisfied. You are making n identical tries of something. So for example, you are throwing a die n times in an identical way, or same dice identically n times. The condition number 2 that must be satisfied for it being a binomial distribution is that in each try a particular event x will happen or will not happen. So you have 2 outcome possibilities. So you have 2 outcomes. And the third, so in each try you have 2 outcomes. And the third condition is that each of the tries should be independent. That means that whatever you do in the first try doesn't affect on the second try. For example, if you throw a die several times, what you get on the first throw doesn't affect in any way what you get on the other throws. Okay, so in this case they are independent. If you instead would have drawn cards from the deck and didn't replace them, then the different draws would be dependent. So that would not qualify, for example. But if you have these 3 examples, it qualifies as a binomial distribution. Okay, so you have 2 different outcomes on each try, and you do n tries, and the tries are independent. Let's say that the probability then is the same in all tries. Let's call it p. Okay, so the p that's the probability for getting one of the outcomes in each try. So for example, given the first outcome in each try, that's the same in each try. Okay, let's now want to figure out what is the probability that the event x will happen in k of the tries. So what is the probability that x will happen in k of these n trials? then that is a binomial distribution and it's given by the following formula. So it's binomial coefficient times p raised to the power of k, and then times 1 minus p n minus k. So this is called a binomial distribution. This is probability. We won't prove it here now, but it's proven in the book because it's a little bit tricky to prove, so I leave it to the book to do that. But we will still see how to use it. So let's now see an example. Okay, let's say that you throw a coin 10 times. So you throw a coin 10 times. And you want to know what is the probability of getting 5 heads, or 5 tails for that matter. So what is the probability for that to happen? Then you can use a binomial distribution, because it is a binomial distribution. We have 10 identical tries. We throw the coin identically 10 times. So it satisfies the first condition. And the second condition, we had that we should have 2 outcomes. And we have 2 outcomes because we have heads or tails. So it satisfies the second condition. And the tries are independent. Are they independent? Yes, of course. If the outcome on the first coin doesn't affect what you get on the other coin, and vice versa. So yeah, all 3 conditions are satisfied. That means that the probability to get 5 heads on throwing 10 dice is given by a binomial distribution. So you have 10 over 5. So this is just the formula we had here. And then it's P. What's the probability? P. P is the probability of getting heads in each of the tries. And that's just 1/2. So here we have 1/2. And that should be according to formula raised to the power of k, that is 5. And then according to formula we should have 1 minus p, and that's 1 minus 1/2. Raised to the power of n minus k, and that's 10 minus 5. So this is just the formula on the last page. And then we just need to calculate this. 10 over 5, that's 10, 9, 8, 7, 6. And then we have 5, 4, 3, 2, 1. And then 10 minus 5 factorial, and that's also 5 factorial. Now we see we can simplify here by cancelling that. And here we have, for example, 4 and 2, that's 8. And then 5 you can take here, so we have 2 there. And this 3 we haven't done anything yet, so we can take it here. So this is 2 times 2, 4 times 63. So 4 times 63. And this is 240, 252. Okay. This was not equal sign, but a side. You did this separately, this calculation. So this was this binomial coefficient. So now this is 252. A half to the power of 5. That is, of course, like this. And this is also half to the power of 5. So it's the same. Okay, so this is 252 divided by 2 to the power of 10. This is 1024, 252. Okay, and if we want to simplify this, what do we get then? We get roughly 25%. Not exactly 25%, but roughly. So that means that the probability of getting exactly 5 heads if you throw 10 coins, that is 25% roughly. So this is an example of a binomial distribution. So you see this is quite an elementary situation, asking what is the probability of getting 5 heads on 10 coins. but the formula itself seems difficult, and the name binomial distribution, but often there is quite central examples you can calculate then. The next example we want to look at is also has a name that sounds more difficult than what it is, and it's called hypergeometric distribution. And that's a complicated name of something that's not so complicated, and actually is useful. Okay, so assume you have n objects. For it to be a hypergeometric distribution, then you should satisfy the following preconditions. You should have n objects, and of these are s special objects. Special means, for example, if I have 10 balls, then 4 of them are red, and then that could be special. So it's not special in that sense, but we have picked them out for some reason. We draw or pick k of objects. So we draw them unordered and without replacement. Okay, so we draw k of them unordered without replacement. And now, of course, there are many situations that we don't really draw things, but if it's equivalent to that, we can use this. Okay, then the probability for the draw to contain x special objects. So we draw k, so the probability for this draw of k to contain x special objects, then it's given by a hypergeometric distribution, and that hypergeometric distribution is given by the following formula. Okay, so this is the formula for hypergeometric distribution. We won't prove it here, but it's proven in the book, since it's a little bit tricky to prove. Not that tricky, but to do it during a lecture. Okay, but let's instead see an example of it. Okay, so let us have an example of a ball of balls. So let's say we have 7 black balls. They're all identical, even if I don't draw them like that here. So 7 black, and then we have 3 red. And now they are mixed up, not like ordered like this, but we will draw them randomly anyways, it doesn't matter. So we have 10 balls, identical balls, apart from the color, and we have 3 red, 7 black. Then, what is the probability that I will draw 2 red balls? So what is the probability I will draw 2 red balls if I draw 5 at the same time? Okay, if you draw 5 at the same time, that means without replacement. Because drawing 5 at the same time, you could just as well draw 1 at a time without replacing. So we draw 5 balls without replacement. Okay, so that's k equal to 5. And then, how many balls are there? There are 10. And how many are special? Now we're looking at red balls. So the special here are the red ones. So there are 3 special. And then we want to consider a case where x is 2, because we want to look at what is the probability of drawing 2 red ones. So now we have an example of hypergeometric distribution. So we have some special and n objects and s special, and we draw k unordered without replacement. Okay, so we draw them here unordered without replacements, because we're unordered because we're only interested in the probability of getting 2 red. And we don't care about order. And also we draw them at the same time, so there is no real order either. Okay, so now we have this formula here. So let's take that, write it down again. So S is 3, X is 2. And this, then we have 10 minus 3. And then we have 5 minus 2. And 10 over 5. Okay, so now 3 over 2 times 7 over 3 and 10 over 5. And the rest now is just calculations. So 3 factorial over 2 factorial, and this is 1 factorial, but 1 factorial is just 1. So now I'm calculating 3 over 2. So we should have a 1 factorial, but that's just 1. Let me leave it as a factorial because a lot of things will simplify. So here is a 7 factorial divided by 3 factorial, and 7 minus 3 factorial, that's the 4 factorial. And 10 over 5, that's 10 factorial. 5 factorial, and 10 minus 5 is also 5 factorial. This simplifies to that. Okay, so now we'll have 7 factorial, 2 factorial, 4 factorial, 5 factorial, times 5 factorial. Here we have fractional division, so we have to flip. So like this. Okay, now I will just write down the answers. So I leave this as an exercise to you to do. It's just writing down all the factorials and simplifying, but it's a tedious calculation. So I just write down the answer instead. And the answer will be 5/12. After everything simplifies, this huge expression will become just 5/12. And that's roughly 42%. So that means that if you draw 5 balls from these 10 balls, then the probability of drawing 2 red ones is 42%. So that's how you can use this hypergeometric distribution. So you see that binomial distribution and hypergeometric distributions, although they sound terrifying names, they're quite elementary examples that you can use them for. But the formulas, of course, are a bit tricky. So that concludes the combinatorial section. So here we have really combinations of probabilities and combinatorics.